Collision theory. So collision theory is essentially saying that for a reaction to happen, you're going to have these particles collide with each other successfully. And so in order for this collision to be successful, there's two things that have to work out. One of them is the geometry, and so it has to have the correct angle. So you can think of a molecule, it could be turned in different ways. It has to be facing the right direction when it collides with the other one. And then the second one is there has to be enough energy in the collision to get that to happen, because if you're breaking a particular force, so easily to think of a molecule being held together with covalent bonds, if you're going to be breaking those covalent bonds in order to create some new particle, you're going to need a certain amount of energy to break that attractive force between the currently attached atoms. So any factor that influences either the geometry or the energy of a collision will have an effect on the rate of reaction. So think of the geometry. If these particles here are to collide with each other, there is a chance that the two chlorines could form a bond between each of them, and you'd form chlorine gas and leave nitrogen monoxide behind. But the geometry is going to have to be correct. If the oxygen hits the chlorine instead of the chlorine hitting the other chlorine, then the reaction's not going to happen. And so the geometry has to be correct. Plus, if the energy has to be right as well, because the chlorine has to be broken off of the nitrogen, that's going to require a certain amount of energy to get that to happen. So we need correct geometry and we need correct energy to get the reaction to occur. 5 factors that actually affect rates are concentration, and essentially with concentration is if you have more collisions because you have more things there, the chances of having a successful collision are going to be greater. Temperature is going to increase the rate of reaction because higher temperatures are going to have, again, the particles moving faster, so they're going to have more energy and you're going to have more collisions, and so again, a greater chance of having a successful collision. Surface area is essentially the same thing as concentration on a particle scale. So essentially you're just increasing the chances of collision, and therefore you're increasing the rate of the reaction itself. Catalysts we're going to look at in more detail, but these guys essentially lower the energy needed to break apart bonds, and so you don't need as much energy to get the collision to be successful, so they will speed up the rate of reaction. And then the nature of the reactant is important as well, because maybe the bonds aren't that stable to begin with. So loosely attracted particles are going to be easier. They're going to require less energy in order to break apart, and therefore to get them to react with something else would require less energy as well. So surface area and concentration. Let's look at this in a little bit more detail. Imagine we have 2 boxes here with some particles in them. If we have, so the same size box, this one here has 12 particles in it, and that one there has, the one on the right has 16 particles in it. So this has the lower concentration on the left and a higher concentration on the right, and so there's just more particles available to collide. There's more collisions happening, and so the rate is going to be faster for the one that has a higher concentration. Just more collisions, faster rate. Surface area, though, is really the same thing. On a particle scale, concentration and surface area are the same thing. And so take a look at this. We've got on the left, we've got 12 particles available to react. So there are here, it's a 4x4 block of particles. So there are 16 there, but it's only the ones on the outside. There's 12 particles around the outside, so like the 4 there, and then we have these guys up there, and these guys down there, and those guys down there. So we're going to have 12 particles on the outside of this block, and they're the ones where other particles could come in and react to them because they're on the outside. The 4 on the inside aren't available to be collided with because they're stuck on the inside there. So low surface area is essentially the same thing as low concentration on a particle scale. When you increase the surface area, so you spread the particles out, it's essentially the same thing as increasing the concentration as well, because now instead of just having 12 particles that are available to react with other particles coming from the outside, you now have 16 particles that are available to react. So on a particle scale, concentration and surface area are essentially the same factor. Transition state theory. So what this is saying is that during a successful collision, there's this intermediate species that is formed that's kind of halfway between the reactants and the products. And so if you think about a reaction happening where you've got to break some bonds and reform some new ones, this is kind of like in the middle. And so we call this the transition state, or the thing that gets created we refer to as the activated complex. And it is really high energy because you're in the process of breaking bonds and you haven't yet formed any new bonds entirely. And so it's going to be quite high in energy and very short-lived. It's kind of in the middle of the reaction. And the energy needed to to reach this transition state, or to create this activated complex, is referred to as the activation energy. So think of a potential energy diagram. We've seen these before where you have your reactants and they form your products. And so the delta H between these two would be a negative delta H because the reactants have more energy than the products. So the difference between the two is moving down in terms of the potential energy. And so think of this as a potential energy graph. This is what we've seen before for an exothermic reaction, but what we need to realize is that on the way from the reactants to the products, we've got to break up some bonds that are holding the reactants in their current conformation or current state, whatever they happen to be. And so we have to put in some energy. Then we're going to get out some energy after the new bonds are forming or the new attractive forces are forming. But this point in the middle is going to be always higher in energy. It's always going to require some amount of energy to do. And so this energy required to go from the reactants up to the activated complex, that energy is the activation energy, or energy needed to create the activated complex. If it's an exothermic one, again, the reactants have more energy than the products, so our delta H is going to be a negative delta H. But there, we must realize that we can't go directly to the products. We also have to put in a certain amount of energy, and that is the activation energy required to get to this activated complex, which is just some sort of species in between the reactants and the products. So in this case here, N2O is reacting with NO, and so essentially we are moving the oxygen from this molecule onto that molecule. So this activated complex would be some sort of thing where your N2O is breaking off that oxygen and is getting attached to this already existing NO, and it's sort of this thing that exists that's really high in energy that is halfway between what it was and what it's going to be. So imagine something like that. So if we're starting with our N2O and our nitrogen monoxide, you'd get this weird looking complex here, which, there's a better picture than one I drew, which is not quite the reactants and not quite the products yet. It's this weird activated complex, the transition state, high in energy. And then eventually you get your products. EA forward is going to be some amount, and the delta H is going to be the energy that you get out because this is an exothermic reaction. There is the reverse process as well. So if you took the energy required to get to the activated complex, that EA forward, and you took the delta H that was the total delta H for the reaction, you could say, okay, well, if I wanted to go backwards, if I wanted to go from the products back to the reactants, I would have to go back up this hill and back down again. And so the energy required would be the sum of the delta H and the activation energy required to make the transition state. All right, let's look at the endothermic one quickly. Again, we would be starting with a set of reactants that is lower in energy, ending with a set of products that's higher in energy. And to get to the activated complex, we would need an EA forward because we're moving forward through the reaction. This would still have a delta H, which would be the difference between the energy of the reactants and the energy of the products. In this case, it's a positive delta H because we're putting the energy has gone higher from what it used to be. As the reactants, it's lower. As the products, it's higher. And so if we did want to go backwards, we would just have to put in this amount of energy here. Oh, that's a little high. This amount of energy here to get back to the activated complex. So that would be the EA reverse, because that would be the amount of energy required to move from the products back to the reactants. To get back up that hill, you'd need that amount of energy. All right, catalysts. Two different types we're going to mention. A homogeneous catalyst is one that is in the same phase as the reactants. So if you have a liquid catalyst and it's working on an aqueous species, that would be a homogeneous catalyst. Or if you had a gaseous catalyst that was in its gas state and it was working on gases, that would be a homogeneous catalyst in the same state or phase as the reactants. A heterogeneous catalyst would be a different one. So if you're driving around in a gas-fueled car still, the gas is being burnt and the emissions run through a catalyst. The emissions are a gas themselves, but the catalyst that we use to make them a little less harmful is a solid, and so that would be an example of a heterogeneous catalyst. What these catalysts do is that when you're doing your reaction, so again, we're starting with reactants. So let's say we're looking at a exothermic reaction. So the reactants have some amount of energy, the products have some lower amount of energy. Our delta H is going to be a negative delta H because the products have less potential energy than the reactants. And normally what would happen is the reactants would have to put in a certain amount of energy. So normally this amount here, that is your activation energy forward. It would be some amount. But what a catalyst does is it says, okay, well, let's try a different route. Let's try another mechanism or a different pathway, doing things slightly different. We're still starting with the same reactants and ending with the same products, but we're going to go through some alternative pathway, and it could be broken up into several steps, or maybe it's just one alternative step. But whatever it is, in order to get the products, its EA is going to be less. And so if we looked at the EA with the catalyst, it would be some amount less than the EA without the catalyst. So the reaction and the delta H is not affected, but the pathway to get to the products is going to be easier or require less energy. It may have more steps to it involved or something like that. It may somehow make it easier to break the bonds, but in one way or another, it reduces the activation energy needed to get to the products. The reaction mechanism. And so essentially what this is the steps that a reaction goes through in order to get from the reactants to the products. And what we've been assuming so far is that the reactants, they either initially they go right to the products. That doesn't happen. They actually form the activated complex and then they go to the products. But again, that's probably an oversimplification as well. It's probably done in more than one step. Those steps that we've been ignoring until now are what we call the reaction mechanism. We're going to talk about the steps themselves as being elementary reactions or elementary steps. And if you were to sum them all together, you get your overall reaction. So reaction mechanism produces reaction intermediates that get consumed in later steps. These aren't the same as activated complex, so they're a little bit more stable than those activated complex. They are actually going to be produced, and then they are going to be consumed again later in the reaction. So imagine methane reacting with oxygen. So C4 plus 2 oxygen molecules is going to form some carbon dioxide and water. But if you were to actually imagining that happen on a particle level, so I think in collision theory, so the chances of having 3 particles collide right in the right spot with the right energy and the right geometry is going to be relatively rare. However, methane burns super easily. And a lot more complex things than methane also burn super easily. So anything that involves more than 2 colliding particles is going to be relatively unlikely to occur all that often. So what happens instead is that it happens in multiple steps. So the mechanism is essentially those steps that are involved in the process of this reaction. One of those steps is going to be the slowest one, and this is where it ties into the rate law. So reactions will happen in multiple steps. We call those steps or elementary reactions. One of them is going to be the sort of hardest one to do. It'll probably have the highest activation energy. It'll be the least likely to occur or require the most energy in order to occur. And this is where we bring in our rate law equation that we were working on earlier. That rate law equation, those orders, those exponents in the rate law equation, they actually tell us which of the elementary steps in a reaction, which one's the slowest. So the rate of reaction is dependent on that slowest step, and the rate law equation is going to tell us which of those elementary steps is the slowest. So these mechanisms, how we come up with them, again, we can't see them happening very easily. It's very hard to test for these little steps that occur between the beginning and the end of a reaction. But our rate law does give us some information based on the experimental data as to which of the reactants slows down the reaction the most or has the greatest effect on the rate of reaction. And those exponents will actually illuminate a little bit of the inner workings of the reaction. So chemists, we're going to use the rate law first of all, and then we can essentially fill in the gaps using our intuition and what we know about particles and what's most likely. But there can be several different answers as to what can be the mechanism, the steps that happen between the beginning and the end of a reaction. As long as you follow these three rules, your mechanism could be possible. So again, there could be multiple mechanisms proposed for any given reaction, but they definitely have to follow this. So first off, no breaking the law of conservation of mass. If each of the steps has to balance. So you can't just create new particles out of nothing. You can't just destroy particles. You got to make sure each of the steps, each of the reactions that happen, the elementary reactions, balance. The second thing is that rate determining step does tell us something, and so we need to make sure that the rate law that gave us the exponents tells us the rate determining step. Then the whole point is to make sure that we end up with the overall balanced reaction. So when you are done coming up with the different steps, they need to add up together to give you your overall balanced reaction. And as long as you follow these three rules for building your mechanism could be possible. So the rate determining step, the molecularity of the slowest step. So remember, we're talking about multiple steps happening between the reactants on their way to become products. It could be happening in multiple steps. One of them is going to be the slowest one. And the molecularity, or essentially the coefficients in that equation, are going to be based on the rate law. Or conversely, if you already knew what the slowest step was, you could say, okay, let's look at the coefficients in the slowest step, and that will actually allow us to come up with the rate law. So if you have the rate law, you can come up with the slowest step, or if you have the slowest step, you can come up with the rate law. Let's try it out. So this question is going to involve mechanisms, that's what we're looking at here, rates, and then we'll draw it on a potential energy diagram as well. So we've seen this reaction here. Two nitrogen dioxide molecules reacting with a fluorine molecule form two NO2Fs. The delta H for this happens to be negative 284 kilojoules, so it's an exothermic reaction. If you were to solve for the rate law based on experimental data, you'd find out the rate law for this reaction is the rate is equal to the rate constant K multiplied by the change in concentration of NO2, and importantly, the exponent works out to be 1 for NO2. So what it's saying is the change in concentration of NO2 has a linear effect on the rate, and it's the same for the change in concentration of F2. They're both first order with respect to NO2 and first order with respect to F2. Those exponents, they are what will help us determine the mechanism for this reaction. Those exponents in the rate law tell us the molecularity or the coefficients in the slowest step of the rate law. So let's try doing this. Let's propose a mechanism for this reaction, and then we'll draw a potential energy diagram to hopefully visualize what we're talking about when we're talking about mechanism. But essentially what we're saying is yes, we're taking these two reactants and they're going and producing this product. However, it doesn't necessarily happen in one go. It might happen in several steps. So think about it when you're building a car out of Lego. So you buy a Lego set for a car. You don't just take all of the pieces and jam them together and you have a car. Essentially, that's the overall process. You start with a bunch of pieces and you end with a car, but the process is broken up into several steps. And it's the same thing for a reaction. So just because we have these pieces here doesn't mean we just jam them together in one go and we end up with a product. There may be several steps involved. So we might have to do step 1 where we might do something, and step 2 we do something else, and step 3 we do something else. In the end, we get the overall equation, the pieces forming the product, but it may take several steps to do that. These steps, that's the mechanism. So let's see how this looks. This so we have here on the bottom our overall reaction. So that's sort of our goal. That's what we need to get to in the end. That's the overall process. Our rate law told us that we have one NO2 reacting with one F2. Those exponents in our rate law, the first order with respect to NO2 and the first order with respect to F2, tell us that there's going to be a mechanism. So I'm going to have, like, let's say this is step 1 here, and I'll do step 2 here. And they're going to sum together, and they will give us our overall equation. But of these steps, let's call this step 1, and let's call that step 2. Of these steps, the slowest one, has one NO2 reacting with one F2. So that is what the rate law tells us. Those exponents tell us what are the coefficients in the slowest step of the mechanism. And I can't change those because that's not what the rate law says. The rate law says one NO2 and one F2. So I'm stuck with that. Let's get rid of those so it looks a little bit better. So other things can happen on the process. So on my way down to get to the overall balanced equation, I can take other steps. But the first one, I cannot change the molecules involved in carrying out the slowest step. Whatever the rate law tells me, that's all I've got. That's the only thing I can work with. The rest of it you get to make up. So imagine we're going to have to end this reaction. We have to make sure it balanced. And then we're going to add in some other steps as well. All of that we get to make up. And by make up, I mean we have some flexibility. We do have to follow those 3 rules, though. They have to balance. The slowest step has to agree with the rate law, so we check that rule is done. Each step has to balance, and in the end, they have to sum up to give us our overall balanced chemical equation. So let's look at this first one. Again, multiple options, but knowing where we're going to go, I can say, okay, well, let's imagine that NO2, let's imagine one of these F's gets joined onto it. So I end up with the NO2 and the F is now attached to it. That would leave the other fluorine as a fluorine radical. So that could happen. It's not the only thing that could happen, but it's possible. I need to make sure that that balances. It does balance, so I'm good in that regard. So I haven't changed the coefficients. So I'm also good in that it still reflects the rate law, because the slowest step, the coefficients of the reactants in the slowest step have to agree with the rate law. So there's a 1 in front of the NO2 and a 1 in front of the F2. That's good. It balances. That's good. I now just have to make sure that I can get to the overall balanced chemical equation with the next step. So maybe I could say, okay, well, let's in the second step use another NO2 and let's have it react with that fluorine radical that got produced in the first step. And I could have them go through a reaction and maybe they'll get stuck together too, kind of like what happened in the first one. And I produce another NO2F. So again, I'm sort of making up what the possibilities are, but as long as they balance, and look at that, it balances, and I haven't messed around with the slowest steps coefficients, I can come up with whatever I want. Use the end result as a guide. So I know I have to end up with, because these have to sum, the mechanism has to sum up to give me my overall balanced chemical equation. I have an NO2 already, one of them. And so if I add a second one, those guys are going to add up to give me my 2 NO2s. So that's great. I know I have an F2 on the left-hand side, and it's going to sum up if I add those two steps, step 1 and step 2 of the mechanism. That F2 will end up at the bottom here. I also have an NO2F and an NO2F, so they're going to add up to give me my 2 NO2Fs. Luckily, this fluorine radical that got produced in the first elementary step gets consumed in the second one, so it will cancel itself out, which is good because it doesn't show up in the overall balanced chemical equation. So this works out as a pretty good mechanism. Let's get rid of some of these lines so we can see that mechanism again. Oh, got rid of too much here. So I had a NO2F and an O there. So as a mechanism, I am leaving the slowest steps coefficients as 1 and 1 because that's what the rate law tells me they are. Those exponents in the rate law are the coefficients in the slowest step. Each equation balances, and the steps in the mechanism add up to give me my overall balanced chemical equation. So it's a good mechanism. I can use that as my proposed mechanism. So slowest step based on the rate law, I need the overall equation. Again, you can come up with more than one mechanism for this given reaction as long as you follow those three rules. Let's get rid of my chicken scratch here so you can see the same information but legible. So this as a proposed mechanism works quite well. It follows all three rules, so it's a good mechanism. Now imagine a potential energy diagram for this. We know the overall reaction is exothermic, so the reactants start with more energy and the products have less. And I'm saying it happens in 2 steps, step 1 and step 2. So step 1 would involve some reaction. This is my sketch here. Step 1 would involve some reaction that produces these products, and then those guys would go through some other reaction and eventually produce the reactants. Let's look at a better diagram than that. So this would be a decent potential energy diagram sketch. I said that this happens in 2 steps. So I have step 1 here and the production of NO2 and F, and I have step 2 here and then the products. The overall delta H is a negative delta H, which is good because it's an exothermic reaction. Another thing is we know the first step of the mechanism is the slowest step, so it makes sense that our first step here has a higher activation energy than our second step. So that should show up in our potential energy diagram as well. Activated complexes, we didn't draw them, but they'd be somewhere between the beginning and end, the reactants and products of each step. So there we have those activated complexes here. And this fluorine is interesting as well. We create this fluorine radical during the mechanism, but it gets consumed again within the reaction itself. So we refer to that as a reaction intermediate. It is not at the beginning of the reaction. You don't see it in any of the reactants. It's not in the products, but it does get produced during the reaction and then consumed again. So it gets canceled out. That's what's known as a reaction intermediate.